Good afternoon, everyone. Welcome to the Tutte Colloquium. Happy to introduce Oliver Pechenik, who's a professor in our department and who recently won the Golden Jubilee Research Excellence Award. And we'll today talk about Tableaux, or Tableaux plural dynamics. Please, the floor is yours.
Yeah, thank you. So we had some debate before we got started about whether the Tableau here should or should not have an X. And I have two different conventions, one here and one on the announcement that went out. And I think this one's correct, but we can argue about it. So I want to talk about these Tableaux, and I want to start by just playing with them over here. So I'm going to think about Tableau. So this is a standard young Tableau. This is a little bit small. Can I make it bigger? Yeah, okay. So what I have here is a grid. I have a 2x5 grid of boxes, and I have filled my 10 boxes bijectively with the numbers 1 through 10. And I have filled them in such a way that both of my rows are increasing from left to right, and all 5 of my columns are increasing from top to bottom. And so this is my standard young Tableau, and I'm going to tell you a thing you can do to it to get a new one. Okay, and the thing you can do to it is you can push this green button. Okay, so I'm going to push this green button, and look at that, I got a new thing. Okay, so this is what we're going to study. We're going to study this process of taking this and turning it into a new thing. Okay, but first I need to maybe tell you what that process was a little bit more. So I'm going to walk it through in some steps. So the first thing we're going to do is we're going to get rid of the number 1, which is a very small number. And now I have this hole in my Tableau, and I'm going to take all of my numbers in my box, and I'm going to sort of shove them left and up to fill in that hole. Okay. And the way in which I want to do this is to preserve the properties I cared about. I care about the rows being increasing. I care about the columns being increasing. So I should slide them around in a way that preserves those properties. So here, for example, to fill this hole, I could try to fill this hole with the 2 or with the 3. But if I try to fill the hole with a 3, then my top row reads 3, 2, 5, 7, 8. Right? And that is not an increasing sequence. So I should not, in fact, slide the 3 into that hole. I should instead slide the 2 into that hole. And that's going to be much better. Okay, so I'm going to do that. Okay, there's the 2. Okay, and now again, I have to somehow fill this hole. I have a 4 and a 5 that could be sort of pushed into there. The 5 is a bad choice. The 5 would sit on top of the 4. That's out of order. I should instead put the 4 into the hole there. Okay, and now I'm along the bottom, so I can just slide the 6 over, slide the 9 over, slide the 10 over. Okay, so now I have sort of percolated this hole through my Tableau. It's popped out the lower right corner, and I'm going to finish up. I'm going to put an 11 in this box, and then I have numbers 2 through 11, but that's not what I want. I want 1 through 10. I'll just subtract 1 from everybody. Okay, so memorize what we have there. It's going to happen all at once. 11 pops in, and they all shrink by 1. Okay, let me go back and do that one more time. Okay, here they were. There they were again. Okay. Do you want to see this one more time through? Yeah, okay, one more time through. All right, so I'm going to make the 1 go away. Oh, so this is my promotion. This is the thing that we did before. I started with this Tableau. I produced this Tableau. Now I'm going to apply promotion again. Okay. So I'm going to delete the 1. Now I'm competing with the 2 and the 3 again. It's the 2. Okay, so the 2 goes in, and now the 5 slides over, the 8 slides over, 9, 10, add an 11, subtract. Okay. So I have a different Tableau than I started with. In fact, I have this other button if I can't tell when they're different from each other, it's just going to mark in what on my iPad looks like pink, but over here it looks like pale blue, which cells have different numbers in them. So you can see what's happening there. Okay. So definition, okay? Any questions about that? This is our key definition, so we want to definitely be on board with it. Okay, so I'm going to apply promotion again. I'm just going to do the green button instead of stepping through it this time. And I get this. I can do it again. I get this. I can do it again. I get this. Okay, so I'm just getting a whole bunch of Tableaux, and they look essentially random, I think, as far as you can tell. You look at them, there's just not very much in common here. We'll do it again, 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 again. Okay. And so now you might think that I didn't code this very well, right? And that something happened to my shaded boxes, but it's not that. In fact, they really are the same tableau, and what's happened is that I applied this operator 10 times, and I actually got the same thing back. Okay. This is, in fact, the same tableau that I started with. Okay. All right, let's try that again. So I'm going to take a new tableau. Here's a new tableau. Is that different? I didn't watch it happen. Let me push it again. All right, there we go. I have a random tableau. I'm going to apply promotion. Oh, I should show the differences. Okay, so this is not the same thing. Let's do it again, and again, and again, and again. 7, 8. Right, you can see here, if you have good eyes, how many times I've done it. 9, 10. Okay, whoa. See, this one's good. This one is actually going back and forth every other one. So it is the case that I did it 10 times and I got back to the same thing, but in fact, every 2 times it was the same thing. Also true. Okay, so that's very nice. In fact, like, this didn't need to be like this. I could try some more exciting example, like, let's see here. Here's a much bigger one, and I could apply this 18 times, and we'll just see what happens. Okay, and it doesn't have to be like this. I could have something bigger, like this. What am I going to do? 4 by 4. All right, here's 4 by 4. Oh, now they're too big. Now you can't see anything. All right, and let's do this. So one promotion produces something totally different. I'll just apply promotion some more times. We expect something nice to happen at 16, and it'll take me a little bit of poking to get to 16, but there it is, there's 16. Yeah?
So the rule is clear when you have like a rectangular shape, but if your shape is like jagged around the edge, where do you?
Yeah, so I'm only going to allow my shapes to be jagged around this edge. But in fact, for this talk, we're mostly just going to talk about rectangles and not worry about that. Yeah, but you can certainly generalize this to more things in correct ways. Yeah. Great question. Okay, so that's what our theorem should be. So let's go back over here and let's see what the theorem was. So this is, oh, also, right, so if you don't want to listen to me anymore, you just want to play with this thing, here's a QR code and you can just push buttons for the rest of the hour. Okay. I'll give you a moment to collect that. So here is this theorem. This is not sort of the first place to realize that this is true, that if you apply promotion once per label, that you'll get back to where you started. But this is a much stronger result that came out around the time I started thinking about this stuff. Brendan Rhodes shows not only if I take a rectangular tableau and I apply this promotion operator once per letter of the alphabet, do I get back to where I started? But it's much better, right? We saw that sometimes you get back sooner. Sometimes these orbits are smaller than that, and you can get an exact enumeration of how many orbits of every possible size. You take some polynomial that I'm not going to tell you what it is. You take some polynomial, you evaluate it at appropriate roots of unity. These evaluations are integral. They're non-negative integers, and these non-negative integers are counting for you these various orbit sizes in this way. Okay. And this polynomial is some kind of generating function for these objects. Okay, so that's a very nice theorem. Unfortunately, the proof is very hard. And the proof is hard in sort of 2 fundamentally different ways. The one thing that's hard about this proof is that it's not really combinatorial. It really is representation theoretic. So what Rhodes does is he realizes this is telling you things about a Specht module, about a representation of the symmetric group, and he can't work with the usual bases we work with on the symmetric group. He needs to know things about the Kajian-Lustig basis, which is hard to work with. And he translates these algebraic properties into combinatorial questions. And then the combinatorics is also fairly difficult. And he has to work pretty hard at the combinatorics as well in order to make that all go out. Okay. This is true. Okay, so one thing we would like is better proofs of this, but other things we would like are sort of extensions of this in various directions. Okay. So where does this come from? So there's a large algebraic context for everything here. But this operation goes back to the 70s, to the works of Schutz and Berger. He's thinking not just about this promotion action where I delete the number 1 and shove things into the corner, but maybe I delete more things. I delete the 1, the 2, and the 3, and then I slide everything. And this kind of sliding operation is computing a lot of things that are important algebraically. It's in computing things about representations of the symmetric group, things about the representations of the special linear group, general linear group, things about cohomology of Grassmannians, and other things as well. Okay. And so I want to focus on this one, except I won't tell you really what it is, okay, but some sort of geometric topological questions I would want to answer. They're computed exactly by taking these fillings of grids and sliding the numbers around and counting things appropriately. Okay. So after this happened, there was a lot of interest in extending the geometry here from, we want to really understand Grassmannians. You want to understand Grassmannians not only through the lens of cohomology, but through other generalized cohomology theories, and one of these is K-theory. And there's a lot of interest in developing analogous K-theoretic combinatorics, and one version of this is due to Hugh Thomas and Alex Young. They exactly took this sliding operation that we had before, and they figured out how you need to change it so that it's computing not cohomology, but instead K-theory. And two things have to happen. One, you have to not look just at the standard tableau that we had before, but some more general notion of increasing tableau. So I'll show you that in a second. And then you need to also generalize the sliding rule in order to make sense of that. And once you've made these changes, it's just exactly doing the right thing for you. It's just computing the corresponding geometric problems. And in particular, once you have this new kind of tableau, you have this new kind of sliding, basically for free, you're gonna get a K-theoretic version of promotion. Or at least when I wrote this down over a decade ago, I thought it was a K-theoretic analog, and now it's not so clear that's really what it is. Okay, somehow the combinatorics is very nice, and the combinatorics, good combinatorics should appear in many places, and perhaps what's really happening here is not so fundamentally geometric, but it is something instead. Okay, so let's take a look at that. All right, so we're supposed to go back to our little applet over here, and let's look at, where did my typer go? Uh-oh. There we go. All right, so here is an increasing tableau. I can make that a little larger for you. So here again, I have a 2x5 rectangle. I have 10 boxes, but I have not filled them with the numbers 1 through 10. I have fixed my alphabet to be 1 through 7. This means I'm gonna have to reuse some of my numbers. But I'm gonna reuse them sort of along diagonals, I guess, like this. I'm gonna reuse them so that my rows are still increasing rows, and my columns are still increasing columns, exactly the way they were before. It's just that globally, there may be things that are the same. And now I need to tell you, again, some sort of analog of this promotion operator. And again, the operator is going to be hitting this green button. So I push this button, and I had this tableau, and I get this tableau, and it's not the same tableau. Okay, we can see it's not the same tableau. And I'll walk you through how you do that one step at a time again. Okay, let's put that back. So the process is gonna be essentially the same. We're gonna attempt to do the same algorithm, except that before I was trying to do this and preserve the fact that I had a standard tableau at every stage, I should have increasing rows and columns. Now I'm gonna preserve the fact that I have an increasing tableau. I should have still increasing rows and columns and not worry about the fact that my numbers may repeat in other places. So first thing we do is we delete the number 1. Number 1 went away. And now I'm going to start sliding. And so right here, there's really no choice to do, right? I just slide, and I slide, and I slide, and I slide, and I slide. And now, what should I put in this box? Well, it should be the thing that turns into a 7 after I subtract 1, so I should put an 8 there, subtract 1, and get this. Okay, let's do it again. I'm gonna go here, the 2 slides, the 3 slides, the 4 slides, the 5 slides, the 7 slides. Okay, nothing really happens. Now here is something more interesting the third time around. After my 1 goes away, I'm very confused about my 2s because I don't know what to do with them. If the bottom 2 slides up, then my top row has 2 2s in it. And that is not really increasing, or it's staying the same. And if my top row 2 slides to the left, then I have two 2s on top of each other. And that's not really an increasing column either. And so there's essentially only one plausible way to fix this, which is to move both 2s simultaneously. So both 2s are going to go into that box and collide, and they just leave 2 holes behind them. Okay, now I have 2 holes I need to fill, but the 3s kind of want, all the 3s want to go in the holes. And I don't really know which 3 is going in that hole, but I don't really care. Okay, I'm going to put 3s in those 2 holes. Okay, and now my 4s are going to go in these holes. And now let's see, 5 definitely wants to slide in here, but 5 also wants to slide up. So it can just do both. Okay, so 5 is going to suddenly develop an evil twin and jump into these 2 boxes. Okay, so I don't worry about the fact that I have repeats. That's free. All I really care about is preserving the increasingness of my rows and columns, and that does that. Okay, and so now my 7 can slide over. And now I can add an 8 and subtract. And I get to this. Seem okay? Yeah.
Sorry, can you go back?
Yeah. To this one?
No, the one before. That one. When did the 3s merge?
Yeah, so I guess these 3s are merging in here, but also there's 3s going in there. So there's a merging and a splitting or something like that. But my 3s are not distinct from each other, so I don't really care which 3 went where. The important thing is that first of all, my 3s are in these 2 boxes, and when I'm done, my 3s are going to be in those 2 boxes. And I'm going to have holes where the 3s used to be. If you want, somehow, it's not really 2 different 3s, it's just one 3 that occupies 2 squares at the same time. It's a very large 3. Okay, so this is this analog of this promotion operator. Okay. And we can check that this is, a different tableau that we had before, and you can sort of guess what we want to have happen. Well, I guess it's not quite clear what we want to have happen. It's not clear whether we want to push the button 7 times or whether we want to push the button 10 times. But we want to push the button either 7 or 10 times, and we push, and here's 5, 6, 7. Apparently we wanted 7. Okay. We don't want 10. If I do 10, if I push too quickly, it zooms. Okay, 10 is not the right thing. Okay. The right answer was 7. Sorry. Okay. Okay, so maybe this was an accident, so you take a different random tableau, and you do this again. And this is okay. Okay, and so maybe that's not convincing enough, so you try to take something bigger. Oh, I don't know, what should my maximum be? There would be 21 boxes, so how about, I don't know, what's a good number? Less than 21?
16.
16? 16 seems like a good number, all right. All right, so there's 16. So I can push this button 16 times. If you believe me, I can just push this one button at the bottom that does it 16 times. But maybe you don't believe that's actually implementing anything, because nothing changed there. Right, let's undo that, and let's just push it literally 16 times and see what happens. So you can see along the way, very weird stuff is happening. Hard to see what these have to do with the initial conditions. But exactly at 16 spots, things did come back. All right, maybe that still seems small. We can take something larger, like, I don't know, something like this. Now you can't even see it, it's too big. Okay, but we can push this button here, which I promise does actually do something. And in fact, nothing has happened. Okay, so now we know what the theorem is supposed to be, right? So I spent a while trying to prove this, and it was sort of sad, because I couldn't prove it. I proved the 2-row case of this, okay, which is where we started. So all 2-row tableaux are in fact fixed if you apply this promotion operator once per box. Okay, and it's a bit better than this. It is like the Rhodes theorem. In fact, sometimes you're going to get back in fewer than q steps. You're going to get back in some divisor of q steps, and you can get an exact enumeration of these small orbits as well. You write down some generating series for these tableaux, and you evaluate appropriate roots of unity. And that's all in there. Okay, so this was very upsetting that somehow I could only prove the 2-row case of this thing that was clearly generally true. But then I realized that I wasn't very good at writing computer code. And the reason I can't prove things is because you can't prove false things. And so here is a 4x4 Tableau. Well, I like it when I can't prove false things. It's very comforting in many ways to try to prove a false thing and not succeed. Here's a 4x4 Tableau. I have 16 boxes, but I've chosen an alphabet of size 11. And let's push this button here, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's almost back. It's almost back. I don't know how well you can see it, but like there's this one number that is not the right number. It's off by 1. Over here I had 3 5s along this diagonal, and then a 6, and here I have 2 5s on the diagonal and then 2 6s on the rest of the diagonal. That's very upsetting. All right, let's push the button some more. Maybe 22, right? That seems like a good option. There's 22, so it's almost right again. Okay, and so we can push the button some more because like eventually this has to work out for us, right? And there it is. So this was very distressing to me when I found this, but in other ways it was very satisfying that I was unable to prove this false statement about this being the same as itself after 11 steps. Okay. So there's somehow something very special about the two-row case. And unsurprisingly, the proof is going to utilize these special properties in order to only prove true things. Okay. So in order to do this, first we need to talk about what happens in the standard Tableau case, because I told you that this Rhodes theorem is quite hard, but in the two-row case, the Rhodes theorem is quite easy. In fact, there's a much easier proof in the two-row standard case, which I think is essentially due to unpublished work of Dennis White, which is that instead of looking at these tableaux, which are kind of hard to think about, and instead of thinking about this promotion operator, which was quite confusing, quite hard to see what it's going to do, I should instead draw some pictures. And so these tableaux are in fact Catalan objects. They're counted by the Catalan numbers. Lots of things are counted by the Catalan numbers. And the correct one to be looking at here is not that, but instead these non-crossing matchings. So this is, I put the numbers 1 through 12 on a circle, and I want to take a perfect matching with the property that none of my edges cross each other. So if I had had, for example, 1 matched with 7 and 2 matched with 8, that would have been not the kind of matching that's allowed. I can't do that. So I have these non-crossing matchings. And what's very nice is that under the appropriate bijection between these Catalan objects, this operation we were confused about upstairs turns into an operation that we're definitely not confused about downstairs, which is called picking up the picture and rotating it 1 tick to the left. So in particular, it's very clear that if I take this thing with 12 boundary nodes and I rotate it 12 times, that it will look the same, because it will be literally the same thing. Okay? And so this is maybe the easiest way to see the order of this action. Okay? And so how do we do this? Well, in each one of these arcs, there's a small end and there's a big end. All the small ends go in the top row. All the big ends go in the bottom row. That's this bijection. Okay, so this is telling you the order of the action, but actually if you want the better version, you want to know how many small orbits there are. Well, a small orbit is going to correspond to a thing that has rotational symmetry. If I want it to look like itself after fewer than 12 clicks, it's because it has some rotational symmetry. And so you just need to count symmetry classes of these objects, and that's not so hard. Okay, so there's a proof of this. Okay. And in fact, you can do better. You can actually upgrade this set of objects to a representation of the symmetric group. So I want to actually act by permutations on these diagrams where I just sort of permute the boundary around. So I could swap if I swap 7 and 8, that would exactly introduce this crossing over here. That's not one of my non-crossing things, but we have these skein relations. The skein relations tell you how to take a crossing and rewrite it as a linear combination of non-crossing things. And if you do this, you actually get a representation of the symmetric group, and not just any representation of the symmetric group, you get one of the irreducible representations of the symmetric group. These are labeled by partition, so there's one labeled by a 2 by C rectangle, the rectangle we've been talking about, and it's exactly that one. It's the one labeled by the rectangle that is showing up in this context. It's everything you ever would have wanted. And it comes not just abstractly, it comes with a basis. Lots of ways to construct irreducible representations of the symmetric group come with a basis. This does not come with the one that you would have learned in your first representation theory class if you took such a thing. It's not the one that you would have built in CO 631. It's a different basis. And in many ways, it's a nicer basis in a few ways. What's the Kajan-Lustig basis here? But one thing that's nice about it is that there's this particular permutation called the cycle, like the sort of canonical cycle of the elements. This acts very nicely. It takes basis elements to other basis elements, maybe with a sign, okay? But it just sends basis elements to basis elements instead of linear combinations, and it just acts by rotating the diagram. I index my basis by these diagrams, and I just send each one to its rotation. Very nice, okay? And so from this, you can get a representation theoretic understanding of what's happening here. Okay, so we want to do this. We're going to do this in this increasing Tableaux setting. And so there's a few ways to prove it, but here's maybe the nicest one, which is not to look at these increasing Tableaux that confused us, not to look at this promotion operator that was confusing with things merging and things splitting apart, but instead to just draw the pictures. And the pictures here are going to be non-crossing set partitions with all blocks being size at least 2. And then everything you wanted is going to work out. So in fact, this operation we had of promotion just turns into literally picking up this diagram and turning it one click to the left. Okay. And so you can see that promotion must get back to itself in 8 steps, because if I rotate this 8 times, it's itself. Okay, the bijection here is a little more complicated. Each block has a biggest thing and a smallest thing and also some middle things. The smallest things are in the top row, the biggest things are in the bottom row, and the middle things are in both rows. So it's not that bad. Okay, and so you can count, you can see the order of promotion, and if you want to know the exact enumeration of the small orbit sizes, it's just counting symmetry classes, and this is essentially known, how to count symmetry classes. Okay. What I didn't know how to do was to build the representation theoretic story, but Rhodes came along a few years later, and he guessed analogous gain relations. Oh, he guessed analogous gain relations for, I can't make the letter N come back, but that's okay. Analogous gain relations for this set partition story. And so there's more than just this one. I'm just showing you one example of these gain relations. To this day, I don't really know how he guessed them. He just came up with these somehow. They're rather amazing. And this allows you to endow this set with the structure of a symmetric group representation. And it is not just any one, it's an irreducible. And it can't be the irreducible for a rectangle, because there's the wrong number of things. The number of these diagrams is not the dimension of any rectangular representation. Instead, you get this one, which has this 2-row rectangle, but it's not the 2-row rectangle you expect, it's a smaller 2-row rectangle. And then instead, you glue the rest of the boxes you need down here into this column. You just get this other thing. Okay. And it comes with a distinguished basis, and the distinguished basis is not the one that you would learn in CO 631, and it's not the one you'd learn probably anywhere else. It seems to be just a totally different basis than anyone had ever seen before. But it's a very nice one, and it has this property that when I act by my cycle, it just sends basis elements to other basis elements by rotating the diagrams in the way that you want. Okay. Well. Okay. So this is very surprising. Somehow, like it becomes representation theoretic, but I don't know how Brendan found these things. I think he just guessed. I think he was just very inspired, and he just wrote down some things and then did a bunch of calculations to make sure the signs worked out the way they're supposed to. It's quite an involved calculation. But now we understand where this comes from, and we understand where this comes from in at least 4 different ways. So with Becky Petrius and Jessica Stryker, we found this distinguished basis sort of sitting inside the space of invariance for some algebra, and simultaneously, it's written a year later, that's publication date, right? Simultaneously and in the Jesse Kim and Brendan Rhodes found this basis, found this module, just arising from the study of fermionic diagonal coinvariance, which they were very involved with, and it just appeared mysteriously in that way. And then later, Jesse Kim found another way to sort of build it out of the basis he already had from the standard Tableaux case. And it really sort of arises naturally in that setting. And then later, in this paper that we spent a long time chasing signs in, with Becky and Jessica, and also with Chris Frazier, we realized how to realize this is living on some Grassmannian in a funny way. So it really isn't a natural thing, just a natural thing you didn't know to go looking for until you chased the combinatorics down. Okay. All right, so that's very nice. That sort of tells you pretty well what the two-row story is. You'll see it really does seem to mean something. It doesn't clearly mean anything about K-theory. You'll see that whatever these words mean, they're in fact sort of more representation theory words than they are really geometry words, and maybe that's really what's going on. This is really a representation theoretic question. Okay. But we want to understand what's going on with more rows, and this seems very hard because we saw, for example, that 4x4 thing that was very confusing, but we're going to try to do something anyway. Okay. So first we're going to change directions a little bit. I'll pick it back up in a second. Maybe this is a good time to ask for questions. Okay. All right, here we go. So unrelated thing, Brouwer and Shriver, back in the 70s, they're studying posets. I don't know why they're studying posets like this, but they are. So they're looking at all the subsets of a poset that are closed downwards, so the order ideals of a poset, and they define an operator on these downwardly closed sets. And they say, given one of these sets, I'm going to get a new one. I'm going to get a new one, and the way I'm going to do one is I'm going to take the complement. Complement is closed upwards. I'm going to take the minimal parts of that. The minimal elements of that are an anti-chain in my poset. They're all incomparable to each other. And I'm going to close that downwards to get a new downwardly closed set. It is a genuinely new downwardly closed set. It's not the one you started with. It's picked up new things. And but it's an invertible action, so you're getting some kind of dynamics on this set. So what happened here, right? So I had this one here, and what were the minimal elements of the complement? It's just this. That's the minimal element of the complement. So I take the closure, the downward closure of that, and I just see these two things. Now the minimal element of the complement is one over here. There's one over here. I take the downward closure, and I get this little L-shaped thing. Okay, whatever. We don't really need to know that. Okay, so they're studying this for some reason. And they prove a bunch of things. So they prove that if I take the product of two chain posets, and here I've written a secret one-element chain poset just to make things look nice later, but really you're taking the product of two linearly ordered sets. This looks like a B by C grid, ordered component-wise. And they check that the order of this action has it's very nice. It's just B plus C. Okay. You might expect weird numbers, and you don't get weird numbers. You get B plus C. And then they did a bunch of computer experiments and got confused. And that's more or less where that ended. And this got picked up 20 years later by Peter Cameron and Dietmar van der Vlas. And they changed the number 1 to the number 2. And they prove the same statement, basically, that on this set of, on this poset, the order of this action is B plus C plus 1. Okay. So I made the 1 go up by 1, and this order went up by 1. That's very nice. Okay. And you might sort of see a pattern going there, and they presumably saw a pattern going there, but then they computed a lot of stuff. They had better computers, I think, than Brouwer and Shriver, and they find that if I take 4 by B by C, then I don't get B plus C plus 3. I get something quite a bit larger than that, and sort of uncontrolled. Okay. But they did have a conjecture here, and the conjecture is that this number you sort of expect to show up, A plus B plus C minus 1, is still relevant to things, that maybe that's not actually the order of the action, but my orbits should be multiples of that quantity. So this number still shows up somehow. Okay. Sort of a weird conjecture. Okay. Well, this sat around for a long time until suddenly we compared numerology and realized that this problem of Brouwer and Shriver and Cameron van der Vlas is secretly the same problem that we've been doing all along. It's actually about these K-theoretic tableaux. In fact, there's a bijection between increasing tableau and these downward closed sets in this product of 3 chains. And the obvious bijection is not the one you want. You want to do a less obvious bijection between these 2 sets. And if you do the less obvious bijection, this will exactly take the promotion operation on one side to the row motion operation on the other side. Okay. And this is very useful because you can take things that are easy in one of these contexts and move them to the other side, and you establish something that was hard on the other side. So you can push things back and forth across this bijection and sort of work wherever it's easiest. Okay. So it turns out, for example, that this theorem about the order of row motion on 2 by B cross C is equivalent under this bijection to the thing I worked pretty hard to prove about the order of promotion on 2-row Tableaux. It's just the same statement, but translated. Okay, but we didn't realize that at the time. Okay, and so from this perspective, you can actually prove this weird conjecture about things being multiples. In fact, you get a sort of more general version. Whatever the orbit sizes are, the orbit sizes can never be relatively prime to this thing that you would have guessed was the size that it was supposed to be. Okay. So in particular, if this number that you thought should be the size was in fact a prime number, well, the only way to be not relatively prime to it is to be a multiple, or 1, but you can't really be 1, and therefore you're getting their thing. Okay. Like, this is very hard to see from the poset theoretic side, but when you translate it into Tableaux, it's much better. Okay, so finally, you may notice that in this list of results, there's the number 1, and there's the number 2, and there's the number 4. And if you go reading through their paper, you'll see very conspicuously that they never mention the number 3. So I don't know exactly what was going on there. Surely they must have computed a lot of examples with the number 3, and I guess they didn't feel confident conjecturing in either direction. Okay. But I have no such scruples, so I'm just going to conjecture. So we just conjecture that, in fact, the order is the small order. Okay? So that, in fact, this 4-row counterexample is the smallest counterexample. So there's 2 conjectures, but these 2 conjectures are equivalent under the bijection before. So you can think about it in terms of this poset theoretic language. You can think about it in terms of Tableaux. Okay? They're the same conjecture. Okay. So the conjecture is that although we have this 4x4 thing where the values went 1 through 11 and the order of the action was 33, this will not happen with 3 rows. Okay. Okay. And ever since 2017, I felt like I was about to be able to prove this fact. And I now feel like I'm very close to being able to prove this fact. So we'll see how that goes. But I think that this time we really are in a place to do it. We're certainly much closer than we were back then. In hindsight, we were not close at all. But it felt good at the time. At the time, we were just like guessing how to do stuff, and now we have more principled ways to go about things. Okay. So I'm going to return to the standard case, because once again, we're proving something special about small numbers of rows, so we need to use something special. And there's a special proof for 3-row standard Tableaux that bypasses all the difficult stuff that Rhodes did, and instead does other stuff that Rhodes did, but easier stuff. And once again, there's a nice bijection between these Tableaux, these 3-row standard Young Tableaux, and some kind of diagrams. So these are no longer Catalan objects, but there's some kind of 3-dimensional Catalan objects. They're in correspondence with something like a 3-dimensional Dick path. And if you look in Stanley's book of Catalan numbers, there's not so many things that are in bijection with these 3-dimensional Catalan numbers, but in fact, there is a pretty good family of these things. They're just more complicated and less well understood. And here's one of them. Here it is. Okay, it's the 3-dimensional analog of a non-crossing matching somehow. Okay. But it doesn't exactly look like a non-crossing matching. But it is a graph, and it's in a disk. And this operation of promotion that was kind of complicated, that was sliding the numbers all over the place, is much easier to understand at this pictorial level. You really do just pick up this picture and turn it 1 tick. Okay, so you can see visually that the order of promotion needs to be 12, or something dividing 12, because I rotate this 12 times and I get back to where I started. Okay. And maybe I get back sooner if it has some symmetry. So you can understand everything in that way. So this was worked out by Peterson, Piliofsky, and Rhodes. These diagrams are due to Greg Kuperberg. Greg Kuperberg was inventing these in the context of quantum groups and trying to write down quantum link invariants. He was interested in the Jones polynomial and the Jones polynomial for knots, and you can think about the Jones polynomial for knots as somehow coming exactly from this picture of non-crossing matchings. And so he said, I would like to do this in other contexts. I will get other things that are like the Jones polynomial, and this will be wonderful. And so he did this, and he found these diagrams. Okay. Although apparently what he really wanted was not these diagrams, but instead the diagrams for type G2. And I didn't realize this until I saw him recently. But I love these. These are, for me, these are the really exciting part. Okay. So these are called non-elliptic SL3 webs. And I'll tell you what they are on the next slide. So they're graphs, they're planar graphs, they're bipartite graphs, and they're not just abstractly planar and bipartite, they actually come embedded. There's a planar embedding up to isotopy, and they come with a fixed bipartition. I don't get to pick how I do it. I'm gonna have all of my boundary vertices be one color, and the other colors need to be then alternating from that, and they're essentially regular graphs, or at least on the interior they're regular. All the interior vertices all have degree 3, but on the boundary I'm not degree 3, I'm degree 1. Okay. And one more condition, that's this non-elliptic condition. I'm not allowed to have any squares. Okay, because I'm a bipartite graph, I can't have odd cycles, but I could have 4 cycles, and I'm not allowed to. Those are bad for some reason. Okay, so these are some 3-dimensional Catalan objects. And once again, you can build this into a representation of the symmetric group. You need some sort of skein relation. The skein relation is essentially this. It's some sort of way of resolving a crossing, and it's that. And you do that, and you get a representation of the symmetric group, and it's not just any one, it's one of the irreducibles, and it's the irreducible that is indexed by the rectangle that is floating around in your problem. So that's all very nice. Okay. This lets you get a very clean, easy proof of these enumerations. Notice I'm not telling you how to get from this to this anymore. Okay. It's a more interesting bijection. If you come to seminar next week, perhaps we will do some of this. Okay. All right, so let's, we want to imitate this proof. We want to imitate this proof for the increasing Tableaux setting. Okay, so I've been trying to do this for the past 15 years, perhaps, and I was trying to do it by just like guessing what pictures I should draw. And I drew a lot of pictures, and I felt like I was drawing the right pictures a lot of the time, and it felt really good, but it never quite worked. The point now is to have a more systematic way of understanding what to draw and understanding why that is the thing that goes with your Tableau and why it should be behaving the way that it's behaving. Okay, and so a lot of the ideas for this were developed in this other context where I'm thinking now about the 4-row case, but I'm thinking about the 4-row standard case. So in the 4-row standard case, we have the Rhodes result, because we have the Rhodes result in all standard cases. But his proof is hard, so I'm gonna have a different hard proof. My different hard proof is going to be a bijection to some kind of combinatorial object, some sort of planar diagrams that spin. And so this is what you do, and you take your Tableau and you take this operation of promotion, and those are complicated, and you turn it into this diagram over here, which is also complicated, but at least promotion turned into something very nice. It turned into rotation. Okay. So once you understand this bijection, which takes a while, at least you can see that the order here is going to be 16 because I can certainly spin this 16 times. Understand what's going on? Okay. So these are called fully reduced SL4 webs. But we're not going to use them. We're just going to use the ideas of how you build this object and how you correspond the object to the Tableau and why they're the same thing. Okay. Okay. So separately, Jesse Kim was continuing to work on this stuff, and he was interested in looking at these other modules that look sort of like the one we had before. So before we had a 2-row rectangle, and then we glued a long leg on it. And now we have a 3-row rectangle, and we glued a long leg on it. And so this is supposed to somehow look like a flamingo because it's kind of, standing on one leg. And he wants to find similar nice bases for these representations that are not the ones you usually get. They're going to be different bases. They're going to be diagrammatic bases, and they should have good algebraic properties. They should have something like skein relations. You should be able to do all sorts of fun calculations with them. And Jesse finds them. He finds them. I'm not quite sure how he found them. I think he guessed again. I think he just guessed what these are supposed to be. And you can see this one is, in fact, almost an SL3 web like we had before. One thing is wrong. It's no longer 3 regular. This vertex here has degree 4. So it's not regular. Some of my vertices have degree 3. Actually, all the vertices have degree 3 plus. For him, all the black vertices have degree 3, and all the white vertices have degree 3 or more. And he has these objects, and it turns out that the number of these objects is exactly correct to be the dimension of this representation. And he can actually write down an invariant corresponding to each one that's actually like producing a basis inside here that works in good ways. It's very surprising. Okay, but this can't actually tell us the Tableaux theory because this dimension is not equal to the number of increasing tableaux. There's not enough of them. But I claim that it is in fact governing some of the tableau. So this is not all tableau, but for some tableau that have the magical property that they match up with Jesse's pictures, in fact, you're supposed to take this tableau and you're supposed to take this promotion action, you're supposed to forget about them, and instead draw Jesse's inhomogeneous graph over here, and you just rotate it. And you just rotate it. And this is the correspondence. And so you can see that for this subset of Tableau, that the order of the action is 10 because this picture rotates correctly under 10 steps. Okay. So this is a conjecture, but I'm quite confident that it's true. And so we're working on this now with Jesse. And so the big development is we thought we could just prove this conjecture, but in fact we can do better, and maybe we needed to do better. Well, we actually know how to draw pictures for all the other missing increasing tableau, the ones that don't correspond to the pictures you drew before. You have more pictures. Okay, so there's some sort of analog of this, but like even weirder looking, and they correspond to all these other increasing tableau, and they all have the property that when I do promotion on the tableau, this is just rotating the picture around. And so you should be able to see the order of the action just by knowing that when I rotate things, they should get back under 360-degree rotation. So this is my idea for this, and I think it's going to lead us to some very interesting representation theory that we have not yet worked out. Okay. Thank you.
Thank you. Any questions?
Do you have any ideas why 3 would be the special number that would break and 4 breaks?
Well, 3 is a pretty small number. 3 is bigger than 2, but smaller than 4. I think maybe after we understand more of the representation theory, we'll see sort of what the small rank miracles are here.
For 4, when it failed, as you showed us, it doesn't fail by very much. So if you had a bigger diagram and you twisted it up like those things you put on your windshield to keep the sun out, do you think you would see that most of it is the same and there's just a small section?
Yeah, I think that's right. I think you're supposed to draw diagrams for those too. But I think they're going to be like, spin 1/2 particles. You have to spin them around 270 degrees, 720 degrees. It's like a belt trick thing. But I don't know how to draw them. And I try not to think about it too hard because I already can't do the 3-row case. But that can be the next 20 years of my life. Yeah?
Yeah, I'm just confused why, like many people.
If you want to be on the recording, we need the mic.
I'm no not sure if this question deserves to be on the recording, but many things seem to be changing in the different iterations of this, but one thing that seems to be the same always is that you're always rotating and coming back to yourself.
Yeah.
For those of us that have never seen this before or don't really understand why, like why is that? Why is it not that like sometimes you have to change to, you know, a sphere and points on the sphere? And
Oh, I don't know. I think the math just likes us.
okay.
Yeah, I don't have a great explanation for why everything is planar, or why all of this mathematics should be planar. But I mean, I guess there are some general facts about like the representation theory of quantum groups that sort of make things want to be planar. But
Thanks.
yeah.
Do you think you have the wrong definition of promotion for increasing Tableaux, and by tweaking some of the edge cases, it would be possible to make the 11 thing work?
No, I think it's the right definition, and I think it's doing the right thing, and I think it's measuring some interesting structure that we have to work out still.
Okay, because
I think this 33 is not a bug. I think it's some complicated
the
feature we need to understand. And so the combinatorics is as hard as it needs to be to describe the things it's describing. Yeah. Because you can also generalize all of this in sort of other directions, and it all comes together very well.
Any other questions? Let's thank Oliver again.